Hi everyone, this is Dr. Nak, and this is a little lecture on section 10.3, and the title is Parametric Equations in Calculus. Okay, so let's first go with the theorem, parametric form of the derivative. It says that if a smooth curve is given by the parametric equations x equals f of t and y equals g of t, then the slope of c at x comma y is given by dy over dx equals dy over dt all over dx over dt. So that will be the first derivative. And the second derivative is given by the derivative of the first derivative, and that goes on the numerator. And the denominator, you're just going to have dx over dt. And of course, denominator cannot be 0, so therefore dx over dt cannot be 0. Okay, so let's do example 1. Find the first and second derivative of x equals cosine cube of theta and y is sine cube of theta. So instead of a parameter being t, I just changed the notation to theta, and that's all. So let's first go with the first derivative. So dy over dx, so that's going to be dy over d theta, because that's our parameter is now theta, and then dx over d theta. Now dy over d theta means that take the derivative of y with respect to theta. So how do I take the derivative of this? So you're going to have 3 sine square of theta, and by the chain rule here you're going to have a cosine of theta. And now let's work on dx over d theta. So that just means that take the derivative of x with respect to theta. So here what we're going to get is 3 cosine square of theta times the derivative of cosine of theta, which is negative sine of theta. Now simplify. So I can cancel out the 3's, and then what do we got? We have sine square of theta and then cosine of theta, whole thing over, I guess there's going to be a negative sign here, and then sine of theta and then cosine square of theta. Now if we simplify this, we're going to get negative sine of theta and then all over cosine of theta, which is same thing as negative tangent of theta. So that is going to be our first derivative. So I'm just going to box this. Okay, so now let's go with the second derivative. So I'm going to write every step out. So d squared y over dx squared. All right, now according to the formula, this is going to be d over d theta. Take the derivative of the first derivative. And then the denominator is just going to be dx over d theta. All right, so let's work it step by step. So our numerator is going to be d over d theta. Now dy over dx, we just computed that to be negative tan of theta. And the denominator, dx over d theta, we already computed it when we're computing the first derivative. So here you're going to get 3 cosine square of theta. Let me toss the negative on the front of it. And then here comes your sine of theta. Let's keep going. So the derivative of negative tan of theta is negative secant square of theta. And then the denominator is going to be negative 3 cosine square of theta and then sine of theta, which gives us, let's just cancel out the negative. Now we got secant square of theta, whole thing over 3 cosine square of theta and then sine of theta. Now 1 over cosine squared is secant squared, so I'm going to bring that cosine squared on the denominator on the numerator by making that into a secant squared. So we're going to get secant fourth of theta, whole thing over 3 sine of theta, which is same thing as 1/3. And then that was supposed to be a 1. Oh, there you go. And then here you're going to get secant fourth, and then 1 over sine is cosecant. And here it is. I think this is good enough, so I'm just going to box that for the answer. All right, now let's take a look at example 2. Find all points of horizontal and vertical tangency to the curve x equals 4 plus 2 cosine of theta, and then y equals negative 1 plus sine of theta, and theta is between 0 and 2 pi. Now the points of horizontal tangency is when the dy over dx goes to 0. I don't know if you remember that or not, but let me just write that out. So dy over dx equals to 0. So if you have a fraction, all you have to do is set the numerator equals to 0, and then you just solve for x and a y. Now for the vertical tangency, this is where the derivative does not exist. So dy over dx does not exist. So that means that if you have a fraction, you set the denominator goes to 0. But anyways, let's try this out. So first step, let's go with the dy over dx. We need to find the derivative regardless. So the formula is dy over d theta and then dx over d theta. Alright, so taking the derivative of y with respect to theta, well, derivative of the constant is 0 and the derivative of sine is cosine. So the numerator is just going to be cosine of theta and the denominator is dx over d theta. So if I take the derivative of x with respect to theta, here what we're going to get is -2 sine of theta. So let me just box this because we need this information to find the horizontal and vertical tangency points. So let's first go with the horizontal tangency. Alright, so this is where the dy over dx equals to 0, so which means that only the numerator has to go to 0. So let me just write every step out. Cosine over -2 sine of theta equals to 0. That implies that cosine of theta has to go to 0. Well, what are those values? Our theta must be pi over 2 and then 3 pi over 2. So let me just box that. Now since we're going to find all points, points means the ordered pair x comma y. So what we need to do now is we need to evaluate our x and a y when theta is pi over 2 and 3 pi over 2. So let's take when theta equals to pi over 2 first. And what we're going to do is we want to compute the corresponding x and then the y value. So our x is going to be 4 plus 2 cosine of pi over 2. And then our y is -1 plus sine of pi over 2. Alright, so now cosine of pi over 2 is 0. So here what we're going to get is 4. And then sine of pi over 2 is 1. So here what we're going to get is -1 plus 1, which is going to be 0. Alright, so it looks like we're going to have a horizontal tangency at 4, 0. Alright, so let me just box this. Now let's go with when theta equals 3 pi over 2. Alright, so then our x is going to be 4 plus 2 cosine of 3 pi over 2. And then our y is -1 plus sine of 3 pi over 2. Now cosine of 3 pi over 2 is 0, so our x value is going to be just 4. And then sine of 3 pi over 2, that's going to be -1. So here we're going to get -2. Let me just box that. So it looks like we're also going to have a horizontal tangency at the point 4, -2 as well. Alright, so let me just summarize it right here. So therefore, we're going to have the horizontal tangency at 4, 0 and 4, -2. Alright, so we're done with the horizontal tangency. Now we're going to go with the vertical tangency. So let's get started on that one. So we got vertical tan. Okay, so that's where the dy over dx does not exist. which means that cosine of theta over negative 2 sine of theta does not exist, which means that our denominator has to go to 0. So let me just write that out. So that implies that negative 2 sine of theta has to go to 0. Alright, so that implies that dividing by negative 2 on both sides, we're going to get sine of theta equals to 0. So when is that going to happen between 0 to 2 pi? Well, that's going to be theta be 0 and then pi. Okay, so from here, since we're looking for all points of vertical tangency, we need to convert this back into x comma y. Alright, so we're going to do the same thing as what we did earlier. So let's analyze when theta equals to 0. Then our x is going to be 4 plus 2 cosine of 0. And then our y is negative 1 plus sine of 0. Alright, so in this case, cosine of 0 is 1. So here what we're going to get is 6. And then sine of 0 is 0. So we're going to have negative 1 for the y. So let me just box this. So it looks like we're going to have a vertical tangency at 6 comma negative 1. Alright, now we're going to do the same thing for when theta equals to pi. So our x is 4 plus 2 cosine of pi. Y is negative 1 plus sine of pi. Now, cosine of pi is negative 1, so what do we get? We're going to have 4 plus 2 times negative 1, which is the same thing as 4 minus 2, so which is going to give us 2. And sine of pi is 0, so here we're going to have negative 1. Okay, so it looks like we're going to have a vertical tangency at 2 comma negative 1 as well. Let me box this and then summary. So therefore, vertical tangency at 6 comma negative 1 and 2 comma negative 1. So let me just box that for the final answer. And this is all what the question's asking us to do, but let's just analyze this for a little bit. So what I did here is I just copied the problem. So x equals 4 plus 2 cosine, and then y equals negative 1 plus sine. And recall that we had a horizontal tangency point at 4 comma 0 and 4 comma negative 2, and the vertical tangency at 6 comma negative 1 and 2 comma negative 1. So remember, there is a relationship between our rectangular coordinate system and our parametric equations. What I mean is that we can always graph our parametric equations on a rectangular coordinate system. So let's first convert our parametric equations into a rectangular form, so maybe we're familiar with what kind of figure that we're dealing with. Figure means graph. Alright, so first, let me just take our x and solve for the cosine, and take our y and solve for sine. So here, if I solve for cosine by using the first equation, we're going to have cosine of theta equals to x minus 4 over 2. And then sine of theta, using the second equation, we're going to have y and then plus 1. Alright. Now, let's use the Pythagorean identity of sine square of theta plus the cosine square of theta equals to 1. So this is just a common trick. And then this implies that we're going to have y plus 1 squared plus x minus 4 squared over 2 squared equals to 1. Alright, so let me just rewrite this nicely. So this is same thing as x minus 4 squared over 4. And then plus y plus 1 squared equals to 1. Now, do you recognize what kind of conic that we're going to get out of this? It is going to be an ellipse. Alright, so this is an ellipse. And center, where's the center? Center is at 4 comma negative 1. and our major axis is going to be parallel to the x-axis. Alright, so let's try to draw this out. So first, center is at 4, -1. So I'm just going to put a dot right here. So this is our center, which is 4, -1. Now, since the major axis is parallel to the x-axis, and the denominator under x minus 4 squared is 4, which is same thing as 2 squared. So this is telling you that from the center, you're going to have to go 2 units to the right and then 2 units to the left. So from here, 2 units to the right and then 2 units to the left will be right here. All right, now let's look at the denominator of y plus 1 whole quantity squared. Well, there is that 1 sitting here, which is same thing as 1 squared. So what we need to do is from the center, we're going to have to go 1 unit above and then 1 unit below. And our ellipse is going to touch all those 4 points. So let me just try to draw that out. I can do this. I can do this. Oh my gosh. I got this. Ah, it's supposed to be an ellipse. Hey, it's not too bad. Anyways, that is supposed to be our ellipse. Now, let's go back and look at the horizontal tangency points and then the vertical tangency points. Now, does it make sense? We concluded that we're going to have a horizontal tangency at 4, 0 and then 4, -2. So which will be 4, 0 and then 4, -2. Do we have a horizontal tangency? Yes, we do. So it makes sense. All right. Now, where are the vertical tangency? 6, -1. 6, -1 will be this point here. And then 2, -1. Now, does it make sense? I think so. So here is our vertical tangency. So what we just did was we just verified our result by converting our parametric equation into a rectangular form and then looking for the horizontal tangency points and then the vertical tangency points. Okay, now let's get into our next topic is the arc length in parametric form. It says that if a smooth curve is given by the parametric equations x equals f of t and y equals g of t such that our curve does not intersect itself on the interval between a to b, then the arc length of the curve over the interval is given by, the notation is s equals integral from a to b square root of dx over dt squared plus the dy over dt squared dt. Let's take a look at an example 3. Find the arc length of the curve x equals e to the negative t cosine t and y equals e to the negative t sine of t on 0 to pi over 2. So the first graph that you see there is the graph of our parametric equations over the interval 0 to 4 pi. Now, since we just want to compute the arc length of the parametric equation on 0 to pi over 2, if you look at the second graph, that piece right there will be the graph of our equations on 0 to pi over 2. So basically what we're doing is this. We want to compute the length of this curve right here. And that is what the question's asking you to do. So let's get started. All right, so our arc length formula is going to become integral from 0 to pi over 2. Let me just write down all the steps. So here you're going to have dx over dt squared plus the dy over dt squared, whole thing square rooted, and then dt. So let's do this step by step by first computing dx over dt, and then we're going to square that, and then we're going to compute dy over dt, and then we'll square that, and then we'll combine them together. Let's first go with dx over dt. All right, so we're going to take our function x and then we're going to differentiate that with respect to t. So notice that we're going to have to apply the product rule here. So it's going to have e to the negative t multiplying here by the derivative of cosine, which is negative sine, and then plus cosine of t multiplying here by the derivative of e to the negative t, which is negative e to the negative t. All right, so let's see what we can do here. So this is same thing as negative e to the negative t sine of t, and then minus e to the negative t and then cosine of t. Since we need to square this, let me just write it as negative e to the negative t. I'm going to factor out the negative e to the negative t, and then here we're going to have sine of t, and then here you're going to have a plus the cosine of t. All right, so that is our dx over dt. Now we're going to square that. So dx over dt whole thing squared is same thing as negative e to the negative t and then sine t plus the cosine t whole thing squared. All right, so that's same thing as negative e to the negative t squared multiplying here by sine of t plus the cosine of t whole thing squared. Okay, now note that, so note negative e to the negative t whole thing squared. This is same thing as negative 1 squared and then e to the negative t squared. Right? So in this case, negative 1 squared becomes just positive 1. And then e to the negative t whole quantity squared. Remember, you multiply those exponents. So here you're going to have a positive e to the negative 2t. Okay, so now let me just rewrite this as e to the negative 2t. And then if I squared sine t plus cosine t, we're going to have to FOIL that out to get sine square of t plus 2 sine cosine, and then plus the cosine squared. I'm not sure if this is gonna help us. I don't know if this is gonna be our easiest form, but let me just box this for now. And we're gonna do the same thing for the dy over dt. All right, differentiating y with respect to t. Again, we're gonna have to use the product rule. So you got e to the negative t, derivative of sine is cosine, plus sine of t times the derivative of e to the negative t is negative e to the negative t. Okay, so let's clean it up a little bit. So we got e to the negative t cosine of t, and then minus e to the negative t and then sine of t. All right, so let me do the same thing here. So I'm going to factor out e to the negative t. And here we're going to have cosine of t minus sine of t. All right, so now let's see what's going to happen if I go dy over dt whole thing squared. So what we're going to have to do is we need to take e to the negative t, cosine minus sine, whole thing squared. So this is same thing as e to the negative t squared and then cosine t minus the sine of t squared. So again, this is going to become e to the negative 2t and then cosine square of t and then minus 2 sine cosine and then plus sine squared. All right, so let me just box this for now. All right, so now what we're going to do is we're going to have to add those two together. All right, so dx over dt squared plus the dy over dt squared. So this is same thing as e to the negative 2t sine square of t plus 2 sine cosine plus cosine squared, and then plus e to the negative 2t. Oh no. And then here we're going to have cosine square of t. I'm going to run out of room. Minus 2 sine cosine. Oh no. And then plus the sine square of t. Alright, so now let me just factor out the e to the negative 2t. So we got e to the negative 2t. And what do we got left? We got sine square of t plus 2 sine cosine plus cosine squared. And then I'm going to have plus cosine squared. Oh, minus 2 sine cosine. And then plus sine squared. Alright, now let's see what we can cancel from here. So we got, I guess we can cancel 2 sine cosines out. Anything else? I think that's pretty much it, no? Alright, so let me just rewrite this as e to the negative 2t. Now, inside of the bracket, I got sine square of t and then plus another sine square of t. So here we're going to have 2 sine square of t, and same thing for the cosine, plus 2 cosine square of t. Alright, so now let me take out the 2. So we're going to have 2e to the negative 2t, and then we're going to have sine squared plus the cosine squared, which becomes 1. So we get 2e to the negative 2t. So now this is going to be, oh, we're not done yet. We still haven't taken the square root, dang it. Alright, so square root of that is going to become our integrand. So our expression here is going to become the square root of 2e to the negative 2t, which is same thing as a square root of 2 times the square root of e to the negative 2t, which is same thing as square root of 2 times e to the negative 2t to the 1/2 power. So in that case, you need to multiply that exponents. So we get square root of 2, and then e to the, what do we get? Negative t. Alright, so this is going to be our integrand. Alright, so I think we're good to go. So let's do this. So therefore, our arc length is from 0 to, was it pi over 2? Of the square root of, let me just write everything out. Dx over dt squared, and then plus the dy over dt squared. Dt, which becomes integral from 0 to pi over 2 of square root of 2 times e to the negative t dt. Get the square root of 2 out of there, then you're going to integrate from 0 to pi over 2 of e to the negative t dt. Alright, as a side work, let's integrate e to the negative t dt. So we're going to let u equals the negative t, du is negative dt, so dt is negative du. So our integral now becomes integral of e to the u, and then negative du, which is negative e to the u plus the constant. And here you're going to have negative e to the u was negative t plus the constant. And now let's plug it back in. So here what we're going to get is, let me bring that negative out in the front of the square root of 2. So I got negative square root of 2 multiplying here by e to the negative t, evaluate it from 0 to pi over 2. Alright, so this is same thing as negative square root of 2 multiplying here by e to the negative pi over 2 minus e to the 0, which becomes 1. So it looks like you're going to have negative square root of 2 times e to the negative pi over 2 and then minus 1. Now use your trusty calculator to compute this value, and I got this value to be approximately 1.12. All right, so let me just box that. So what we concluded was that the length of that curve is approximately 1.12 unit measured. It sort of makes sense because if I draw a straight line through at the endpoints of those curves, that length should be less than the arc length that we just computed. So I already just computed the distance of that straight line, which is approximately exactly square root of 1.04, which is approximately 1.02. So again, it kind of makes sense because the straight line there should be shorter than that green curve. Anyways, I'm going to stop here for lecturing 10.3. So if you have any questions at all, you know where to find me. And good job, everyone. Good work.